Alright, so today we're going to finish up looking at the individual transformations. So by individual, I mean every problem I've given you yesterday for homework and today for homework. It's just a single transformation per problem. So we'll finish up those today. Tomorrow we'll start looking at combining, right? Doing multiple transformations in the same problem, and a few other things. All right, so first thing I want to talk about is what has to do with the vertical stretching. Okay, we did shifts yesterday. We're going to look at stretches today. So the height of a sine or a cosine wave, that's called the amplitude. And the height is measured from the center to the top, but it's also symmetric if you draw in a center line to the bottom. Now, since the amplitude is measuring the height, what kind of number do you think it has to be?
Positive.
Has to be positive. Okay, you would never say this graph has a negative amplitude. That's like saying negative distance. Okay, so any questions on what amplitude measures? Now, when we start talking about other functions that are not waves, like the graph of tangent, I think I showed that yesterday, it kind of was these curved things. We don't really talk about amplitude anymore, because the graph of tangent goes up and down forever. Okay, amplitude really only applies to graphs that do not go up and down forever. Okay, so amplitude change. Anytime you do a stretch, that's when you multiply. Where do you multiply for amplitude? Outside the function, okay? In front. So we had square roots. That's a vertical stretch by a factor of 2 for a square root. That's a vertical stretch by a factor of 2 for a log function. That's the sine function stretched by a factor of 2. And remember, vertical, what you see is what you do. A bigger number would stretch the graph bigger. A fraction, like that, would compress the graph. So vertical, it's exactly what you would expect. That's also an amplitude change. But now something else is happening. Does anybody remember what happens when you put a negative with the number that does the stretch? It flips. So this graph is doing two things. It's becoming twice as tall, and then it's flipping vertically. So if I give you a graph or an equation, and all I ask you about is the amplitude, I just say, what's the amplitude of this? It's the absolute value of the number in front. So for the thing I just circled, what's the amplitude? 2. What's the amplitude now?
2.
Still 2. Putting a negative has no effect on the question, what is the amplitude? What the negative does do is change the graph. It causes it to flip. Okay? The only time you take the absolute value is if I ask you, what is the amplitude? Don't give me a negative number. But when you're sketching it, you have to include the negative, because the negative does cause the picture to flip. Okay, we already said that. Amplitude's always positive. So amplitude change is going to stretch or compress the axis up and down. So before I play what that would sound like, I just want to see if anybody has an idea of what they think it would sound like. So pretend you had this sound wave and then compared it to that sound wave. What do you think the difference would be between the two?
High pitched.
Okay, that's one thing that can change about a sound. And we are going to talk about that today. Either we're doing it right now or we're going to be next, one or the other. So you can change the pitch. What else can you change about a sound? Yeah? The speed of the sound.
Like the,
So the speed of sound is pretty much dependent on, among other things, the medium it's traveling through. And if it's traveling through air, the temperature. So for example, if you had a, let's say a 500-foot long steel rod, and you put it on the ground, and you put your ear right on the end of the rod, somebody on the other end of the rod hit it with a hammer, you would hear it twice. You would hear it once through the steel rod because sound travels very quickly through a solid. And then if you lifted it real quick, you would hear the sound again through the air. Sound travels much slower through the air than it does through water or something solid. So so the speed of the sound won't change unless we change the way it travels or the temperature of the air it's traveling through. But what else can you change about a sound besides the pitch? Yeah? The volume. Okay? So in this case, it is a change in volume. Okay? Okay, change in volume. Okay. All right, so let's try an example of that. So here's a tone that's 1,000 hertz. Just give the speaker a second to Bluetooth. And now, what I'm going to do is I'm going to put the volumes together. So I'm changing the left and the right speaker at the same time. And I'm going to stretch it and compress it vertically. So it gets louder. And then it gets softer. So that's the change in amplitude. It affects the volume. I think a much more interesting one is when we start stretching and compressing left and right. Then we can change frequency. So then we can do some interesting things. All right, so find the amplitude. You don't have to sketch it. Just want to know the amplitude. Okay, so equation, amplitude. What's the amplitude of A? 3. Okay. It has an amplitude of 3. What if I did this?
3.
Still 3. What if I did plus pi?
3.
Still 3. That plus pi, I've done a phase shift, but that has nothing to do with amplitude. That's what we did yesterday. Okay? So you can change all kinds of other things, but make sure you know what number to focus on for the amplitude. So there's your equation on the left. What's the amplitude there? 4/3. What's the 6 doing? We talked about that yesterday. That's shifting it up 6. The pi over 2, what kind of shift is that? That's, a phase shift. It's moving it left. The only thing that's actually affecting amplitude, 4/3. Okay. How about -2 sine x? 2. What if I get rid of the negative?
2.
Still 2. But does the negative have an effect on the picture?
Yes.
Yes, it doesn't have an effect on the amplitude, but it has an effect on the picture. If there's your graph, there's the negative of it. Okay?
Wow.
So you're just taking the graph and flipping it. Okay. So to determine the 5 points, remember we got that table, we got to figure out where the 5 points go. Of the 2 transformations, this is the easier one today. Stretching up and down. What values does that change? Changes the y's. So the x's stay the same. Why is it nice when those stay the same? Because those are all the fractions with pi. You don't have to mess with any of them. So for every amplitude problem we do today, here's the answer to the x's. 0, pi over 2, pi, 3 pi over 2, 2 pi. For every amplitude problem today. Okay, the y's. What are the numbers that are in the y column? There's only three numbers, whether you're talking about sine or cosine, that are in the column.
The max, min, and the middle.
And what are those?
The limits of the.
Well, the actual numbers, like 5, 6, and 7. Yeah. 1, 0, negative 1.
I would say raise my hand.
So all you have to do is arithmetic with a 1, a 0, or a negative 1. Very easy. Okay. To find the new y values, multiply the old ones by c. Okay, and if you're like, well, wait, what was c again? C is the number that's in front of the sine or the cosine.
So the amplitude?
Sometimes.
Sometimes.
Why did I say sometimes? He said, well, is it just the amplitude? And I said, well,
Wait,
sometimes.
so C is not the same as the amplitude?
Right. C is not always the same as the
If
amplitude.
it's related to the graphic.
So you're just doing.
Here's an example where C is not the same as the amplitude.
Oh, yeah. I see.
Right? The amplitude is 2.
So if it's negative, you would multiply it by the negative.
Exactly. If it's negative, you have to use the negative when you're graphing. The only time you don't use the negative is if they ask, what is the amplitude? Because don't say it's negative 2 feet tall. It doesn't make sense. Okay. Negative affects the graph. Negative has nothing to do with the actual amplitude. Okay. So let's take a look at a couple examples. Okay, 3 cosine x. So first thing on the test is I'm not going to tell you what that is. You have to look at it and know which one of the 4. Okay, so that's a vertical stretch. How do we know that's a vertical stretch?
Because it's not. Oh wait, no, crap, sorry. Because it's on the.
It's in front, and what operation are we doing? Multiplication. You're multiplying by a number in front. Okay, vertical stretch. What stays the same? X's. Hopefully by now we're starting to know these. For cosine, what are my y values? Make sure you don't give me the sine units.
1, 0, 1, 0,
1, 0, negative 1, 0, 1. Now, what are we going to do to all those values? Multiplying by 3. Yeah, triple them all. So 3, 0, negative 3, 0, 3. There's your table. Okay, so actually I think I already have graphs set up. Okay, question on the table. All right, so now when I set up my graph, what I can do is I can go by 3s. The axis is 0, 3, negative 3. And then my values on the y column, well, I've got 0, pi over 2, pi, 3 pi over 2, 2 pi. Yes, you have to label that. Okay, if you don't label the, if you don't label an axis, I'm going to assume you're going by 1s, because that's what you usually assume. Okay, let's make our graph. So we've got 0, 3, pi over 2, 0, pi, we're at negative 3, 0, back to 3. Okay, this is the one that sometimes people make it straight, but remember, it's the middle part of a wave, so it is a V shape, but it's not, it doesn't come to a point. Kind of something like that. And that's your sketch. Okay, any questions on that one? Now, because I've changed my scale, watch what I could do. Let's say I wanted to graph 5 cosine x. I could use that exact same picture and just go like this. 5, negative 5. So if you're look at that and you're like, well, geez, a lot of these graphs are looking the same. A lot of my graphs are going to look the same because I'm going to change the scale every time. If you change the scale, the picture stays the same. Okay. Any questions on that? Okay, so that's a vertical stretch by a factor of 3. What kind of sound would that be again if it's stretched? Louder. Yep. Okay. What's happening here? 1/2 sine x.
Make it smaller.
Right, it's going to compress it. So if that was a sound, it would be a softer sound. If that was like a radio signal, because radio signals are also waves, that would be a weaker signal. Okay, it wouldn't be as strong. Okay, so we're compressing it vertically. What stays the same? And yep, can you tell me what they are, Curtis?
Yeah, there's 0, or, no, yeah, 0, pi over 2, pi, 3 pi over 2, 2 pi.
2 pi. And now we're going to take the original y's for sine and take half of them. So originals are 0, 1, 0. Well, I'm not going to write them because I'm running out of space. Just take half of all the originals. 0, half, 0, negative a half, back to 0.
Wait, what are the numbers again? 0, 1, 0.
The original y values for sine, 0, 1, 0, negative 1, 0. And I took half. Okay, any questions on that? Okay, now when I sketch this, you might be like, well, it looks the same as the regular one. Mine is going to look the same because I'm going to change the scale. I'm going to make that 0, a half, negative a half. That's not the only way to do it. If you want to do it a different way, that's fine. Got 0, 0. I'm going to put my y-axis labels above this time. Pi over 2, pi, 3 pi over 2, 2 pi. It usually works better if you put them above or below. If you try to put them right in the middle, then you end up drawing right over them. Half, 0, negative a half, back to 0. Okay, so there's your vertical compression. Okay, compressed. I guess you could say it's stretched by a half, but that really means it compressed. Okay, any question on that one? Okay, last one for vertical stretch, and then we're going to look at stretching and compressing the other way. Okay, what's the amplitude of that function? 1. So that's what the amplitude always is. So technically, this is not an amplitude change. The amplitude is not changing, but something's happening.
It's negative.
What's the negative going to do?
Flip it.
It's going to flip it. So all the y values that were positive become negative. All the negatives become positive. And if you're like, well, how does that really fit in with multiplying by a number in front? What number is in front, even though I didn't write it?
1.
Yeah, it's like you're doing negative 1 times cosine. So it still fits the pattern of multiplying by a number in front. It just doesn't change the height. Okay. So x's stay the same. And can anyone tell me what my y values will be? And keep in mind we have to make them all negative.
0.
So negative 1, yep.
0, 1, 0, negative 1.
Yeah. So normally the cosine part that we sketch looks like a V shape. This is going to look more like an N shape. It's going to be flipped over. Technically, you don't have to label your y-axis here, because I'm going to go by ones. But if you want to, you could. Definitely need to label my my vertical labels. I need those. So pi over 2. Okay, so fill those in. And we're at negative 1, 0, 1, 0, negative 1. Okay, and remember, this If you get confused, think about you're sketching something like that. It's the middle part of the wave. And it would continue on. You don't have to draw the dotted part.
Can you do one more like that?
A flip one?
Yeah.
If we have time at the end, I can do one more. Yep. If not, I'm sure I have one I can show you. Okay. So, any other questions on that one? Right, so that's pretty much all the kinds of amplitudes you could have. A stretch, a compression, and a flip. All right, last type of transformation, period change. So now we're going to change the period. So remember, the period is basically the amount of degrees or radians you have to go through before the graph repeats. If you compare something like that to that, one of them has a very short period. It's cycling quicker. The other one is cycling much more slowly. What's the normal period? If you don't mess around with it, it goes from 0 to 2 pi. 0 to 2 pi is the amount of radians you have to go through, and then you repeat. Well, now we're going to affect that. Sometimes we'll shorten it. Sometimes we'll lengthen it. So now when we do a stretch, what operation is it? Is it addition or multiplication? Stretches are always multiplication. Shifts are always addition or subtraction. But we already multiplied in front. That was outside. Now we're going to multiply inside. Okay, so this is the difference between 2 square roots of x, which is a vertical stretch, and the square root of 2x, which is a horizontal. And remember, with the horizontal, everything is reversed. Yep, could you just sign out for me? Thanks. So horizontal, everything's reversed. So what that means is, if you put in a big number, you might think, oh, big number is going to stretch the graph out bigger. Well, let's try and see. Let's do it on the calculator to do it quick. Let's do sine of x, and let's do sine of 5x. Okay, so at first you might think, well, maybe it's going to stretch it out 5 times as big. But if you watch, that's not what's going to happen. There's the original. And here's sine 5x. So what did the 5 do to the graph?
It increases slope.
Compressed.
It compressed it, right? If you think of that blue thing as like a spring, you compressed it, right? Now, if you wanted to stretch it, what kind of number do you think you would put in front of x? A fraction. If you did like 0.5x, okay, anything less than 1 is going to stretch. Okay, and now you'll see it as it sketches it. So it's been stretched out. So big numbers compress the graph, small numbers stretch it. So for what we're going to do is we're only going to look at examples where the number in front of x is positive. It could be negative, and if it was negative, it would be a flip. Okay? But we're just not going to look at graphs that flip horizontally. We are going to look at graphs that flip vertically. We just did that. But not horizontally. So period change stretches or compresses the graph along the x-axis. And just to be clear about what kind of numbers do what, numbers bigger than 1 compress it. The bigger the number, the more the compression. So if you graph sine of 50x, you're going to compress the graph 50 times as much as the original. If you graph 0.5x, that's going to stretch it. Okay, so greater than 1, compressed, less than 1, stretches. Okay. Now what I'll do is I'll play some different sounds for you to hear. And it's always interesting because we can kind of see who can hear different frequency sounds. Right, so I'm going to start out with 1,000 hertz. In the scheme of frequencies, not a high-pitched sound at all. And I'll keep the volume right around 24 or so. It's got to connect. How many people heard that? Anybody not hear that?
You again.
You didn't hear it?
No, I just.
Not your name.
We got it. Okay. So now I'm gonna bring it up a little bit. So now this is 27, a little over 2,700 hertz. So this sound, if you look at it on an oscilloscope, is cycling 2,700 times per second. And I don't want to play two different sounds. I want to play the same sound from the left and right.
I did not like that.
So we're getting higher, but we're nowhere near high pitch.
No.
So we're going to play 7,000 hertz.
Oh,
You might notice it sounded a little softer.
that was.
Some people,
I think a dog just cried.
as not yet. As you start to get higher pitch, it gets harder to hear. So it might sound like I'm lowering the volume, but I'm not.
That tone messed with my vision, man.
So up around 12,000 hertz.
You used to set this up in my class with my pods.
Getting a little higher. Let's try 16,000 hertz. If you don't like it, block your ears.
That's my jam right there. 24 hours straight.
Now that one, I lost that one. I can't hear it.
It's like cut knife.
And it just happens when you get older, you just can't hear the high pitch.
Oh.
Anyone else that couldn't hear it?
That tickled my ear.
Can you do it again? It kind of like, it's really like faint, I feel like.
Yeah, so if that one was faint, then if I go a little higher,
Go all the way.
probably lose it.
I can't hear anything.
I can hear it.
I can't hear anything.
Oh wait, it's not on.
And then it's about as high as I can go.
I can hear it a little bit. You know it's buzzing.
Yeah, you can hear it a little bit.
Yeah, like a little fuzz almost like.
I
I
can't
don't
hear
know how to
anything.
describe it, but
And then
it's called mine.
on the opposite end, we can play a lower pitch frequency.
Whoa.
That was weird.
Dude, I
So with a low pitch sound, you start to feel it. Okay? The higher pitch frequencies that I was just playing, they didn't hear them in the other room. High pitch frequencies don't travel well. The low pitch sound that I just played, they definitely heard that in the other room. And there's certain objects in this room that's kind of interesting around, like 56, 57 hertz. If you play it loud enough, certain things start vibrating. So you probably felt something vibrating, but there's something in the ceiling that, I'll just show you. And I'm slowly going to go up to 57, or 56. It's right around there. Something's resonating. What's that?
like the bass in my car.
Oh yeah.
I like, that's like music.
Wait, put it back on.
That made me like sleep.
57?
Oh yeah.
Just getting ready for takeout.
I think it's like a vent over there.
Yeah, it might be the
Do it one more time.
But then if you just change it to 58, it won't do it. It'll stop. It's actually a little different.
There's a vent over there.
And you can go a little bit lower Okay, you can go all the way down to 1 hertz, and it is still plural, it's not hert. But I can't play that because my speaker can only go down to 45, and I did 50, so that's about as low as I can do. All right, so when we start stretching and compressing it, we're changing the period. Okay, so what I'm going to be asking you, kind of like the amplitude, is what is the period? Okay, you don't have to sketch anything. Just tell me what's the new period. Okay, and the formula to find the new period is 2 pi divided by b. Okay, and if you don't remember, what's b? B, the number in front of x. Okay, so just to make it clear, the period is not b. B is the denominator to find the period. Okay? The period is 2 pi divided by b. Okay? So let's try one kind of like finding the amplitude. You don't have to sketch it. Just tell me the period. All right. In example A, first of all, what is b? 2. 2 is not the period. 2 is just b. And where does the b go? Bottom. Denominator. So what's the period of that?
It would be.
Pi. What's the normal period? Before we messed around with it?
2 pi.
2 pi. So we just shortened it. Pi.
How's that?
Because we put a 2 in front of x, and that caused it to shorten. So normally this graph would have to go, if I did it as a decimal, from 0 to 6.28. That's 2 pi. Now this graph is going to do its thing from 0 to 3.1. So it's been shortened, period.
All right.
Okay. How about b? What's the number in front of x here?
1/3.
1/3. Is that the period? Is 1/3 the period?
No.
No. 1/3 is just the denominator. That's b. It's 2 pi divided by 1/3. Can you just check back in here? Oh yeah. So how would you divide 2 pi by 1/3? What do you do? Multiply by what? The reciprocal. 2 pi times 3. How much is 2 pi over 2 pi times 3?
6 pi.
6 pi. So by putting a small number in front of x, it made the period bigger. That's how it works. In fact, how much bigger did you make the period? If it was 2 pi, now it's 6 pi.
4. 4 times.
Not 4 times.
6 times.
6 times. No, not 6 times. 2 pi to 6 pi.
4.
3 pi.
3.
5.
3 pi.
Oh, 2 times. Whatever.
So the period started at 2 pi. By multiplying by 1/3, you stretched it out 3 times as much.
Can you do the sound again?
If you have time at the end.
That sound really like was
I missed it.
What time?
Okay, what's the period? You didn't hear it in the bathroom?
Yeah, I was
You didn't hear it though there?
no.
Oh, okay. Well, good. It's not that loud then.
I wasn't looking for it. I mean, I
What's
was looking for it.
what's the fraction I would set up to find the period this time?
What do you think
You're pretty cheap.
that pi?
Yep. Brandon, what would be the fraction?
A number. I wasn't paying attention. I apologize.
Fraction.
What goes in the top of the fraction?
2 pi.
2 pi always goes in the top. What goes in the bottom?
Okay.
Not x, but what's in front of x.
1.
And what's in, well, not here. There's no 1 in front of x there.
Pi.
Pi. So what's the period of this one? 2. So this graph doesn't have pi in it. It's going to go from 0 to 2 and do the pattern. And then from 2 to 4, It's going to do the pattern again. Every 2 units, it's going to repeat. How about last one? First, tell me what number there has to do with the period.
3.
Just the 3. We've got a vertical stretch and a vertical shift. Those have nothing to do with the period. What goes on top to find the period? 2 pi. What goes on the bottom?
3.
3. That's the period. Okay. Period is kind of like amplitude. You would never have negative period. And I said to you that number in front of x will never be negative anyway. So that'll never come. Okay, so last thing we have to do is graph period change. Okay, for period change, what is staying the same? What column? The y's, right? Period change, we're stretching and compressing left and right. So the y's are going to stay the same. Well, unfortunately, the y's are the easy ones, right? Those are the ones and zeros and negative ones. So now we have to work with the x's, okay? Those are the fractions with pi. So 2 of the transformations are easy. 2 of them involve a little more arithmetic, and this one involves a little more arithmetic. Although it's not bad. To find your new x values, just take the original x's and divide them by b. That's it. Take the original x's, 0, pi over 2, pi, 3 pi over 2, 2 pi, and divide them by the number in front of x. So most of the time, that means you're going to have fractions over fractions. And what do you use when you have a fraction over a fraction? Reciprocal. Okay? Okay, does everybody have the 2 steps that want to copy it for a period change? Okay, so let's look at this one. Sine half x. Now we know all the transformations. Okay, we studied each one of them individually for trig functions. We've studied them all before many other times. How do we know that's a period change?
Because it's multiplying.
Okay, that's a big hint. It's multiplied, and where? Is it out in front or inside?
Oh.
Inside. Okay? When you multiply inside by the x, that's your period change. Okay. So remind me, what stays the same? Y's. What are my y's for sine?
0, 1, 0,
0, 1, 0, negative 1, 0. Now, I'm going to put the original x's, but I'm not going to divide them yet because I'm going to put them in the table for the final answer. What are my original x's?
0.
0. Pi over 2.
Pi. 3 pi.
And last one?
2 pi.
Okay. Now, what are we going to divide all of them by? B. But what is B in this case? 1/2. So, dividing something by 1/2, that's what we're supposed to do. But there's an easier way to think about it.
Multiplying.
Doubling everything.
Told you.
Right? Dividing by 1/2 is the same as doubling everything. Double 0, what do you get?
0.
0. How about if you double pi over 2?
2 pi over 2 is pi.
2 pi over 2, which is just pi. 2 pi. 3 pi over 2 doubled.
6 pi over 2, which is 3 pi.
3 pi, yep. And 2 pi doubled.
4 pi.
4 pi. Any questions how we did any of those doublings? And if you do it right, you should see a pattern. 0 pi, 1 pi, 2 pi, 3 pi, 4 pi. If you look at it and you get a pattern like 0 pi, 1 pi, 5 pi, 6 pi, and it skips kind of funny, something's wrong. Okay. Okay, what's my last step?
Graphic.
Graphic. Every y-axis you can label like that for every problem in this part, because you're never going to have anything other than ones and zeros. My other labels, that's 0, pi, 2 pi, 3 pi, 4 pi. Are those labels nicely spaced? Yeah, of course. That's 0, 180, 360. They're all 180 degrees apart, but we're doing it in radians. 0, 0, pi 1, 0, -1, back to 0. And if you look at that and you say, well, doesn't that look like every graph? Yep, doesn't look any different. Because what did I do that makes it look the same as everything else? I changed my scale. Okay? I normally do not use these labels, but I did this time. And my graph looks the same. Okay. Questions on that? Okay. Anyone need to copy anything from that one? Grading on that kind of problem, it's exactly the same. 10 for the table, 1 point, 2 points for the graph. Whatever makes it work out on the test. Okay, cosine 2x. Actually, you know what? Why don't you try that one? Take a minute, 2 minutes, see if you can figure out the table there. Yep. And if you have a question, I'll come by and help you out. Okay. As you go through a period change, if you don't shift it left and right, you can fill that in right away. Because the first x is 0. If you take half of it, it's still 0. If you double it, it's still 0. If you triple 0, 0. So unless you shift left and right first, your first x value always stays 0. What about my y's for cosine?
1, 0, 0.
And now, what are we doing to all the x's?
Divided by 2.
Dividing them all by 2, which is the same as what? By a half. So the first one, 0 times a half is 0. The next one is pi over 2, and you're dividing it by 2, but I don't want to think of it that way. Think of the reciprocal. So what do you get if you multiply straight across? Pi over 4. The next one is pi. And what are we multiplying it by? 1/2. Multiply straight across, what do you get? Pi over 2. Now, if you wrote everything with a denominator of 4, you'd see a pattern. 0 pi over 4, 1 pi over 4, 2 pi over 4, but it's reduced. What's the next one? 3 pi over 4. And the last one is 4 pi over 4, which we reduce to pi. So I always try to just do the first 2 or 3 and then find a pattern, and that usually speeds it up. Hey, any questions on what the sketch would be for that? Or does anyone want me to do the sketch? You just label it. And this one's going to look more like the V shape because it's the middle part of the wave. Okay, last one. So you look at that number in front of x and you're like, oh my god, pi over 3. This is actually going to be the nicest numbers we've had to work with in the final table yet. Okay, so we just did a cosine. Let's fill in the y's. 1, 0, -1, 0, 1. The first x value, if you don't shift left and right, is always what? It's always going to be 0 unless you do a phase shift first. Then it won't. Okay, what's the next x value after 0? Pi over 2. And what am I dividing pi over 2 by? I'm dividing that by that. So that really means to take pi over 2 and multiply by what? 3 over pi. What happens there?
3 pi.
We have 3 pi over 2 pi, so what cancels out? Pi. So what do you get? You could write, yeah, one. If you want to put 1.5, that's fine. And now technically we know every one of them is equally spaced, and the spacing is 1.5. So what should the next one be? Should be 3. Let's check it, and then if that pattern works, we'll just fill in the rest. The next one after pi over 2 is normally, what's right after pi over 2? Pi. And you're dividing it by pi over 3. So let's multiply by 3 over pi. What cancels out? The pi's. And you're left with 3. So now I think we can go by the pattern. Next x value. And the last one. 6. So I told you this table would be the nicest numbers we've worked with, and it is. There's no pi's in any of those numbers. Okay, to graph it, let's finish up with the graph. We've got 0, 1, negative 1. And actually, you know what? If you don't label anything here, you could probably just go by ones. 0, 1, 2, 3, 4, 5. Do we need 6? Yep. 6. Right, so we've got 0, 1, 1.5, 0. 0.5, I mean, it's not the nicest number, but it's not that hard to estimate. 3, negative 1, 4.5, 0, 6, 1. Here's your graph. So what does the graph normally have to go to before it repeats? What's the regular period? 2 pi, which is about 6.28. Well, this graph has to go to 6. So it's shortened, but just a little bit. Okay, it's normally 6.28. This is 6. That's not much of a compression at all. Okay. Any questions on that? All right. The homework tonight will be these 8 questions. Again, I have them on a worksheet, but if you lose it, it's on